And so in red you have baseline, in yellow you have the observation 30 minutes after medication intake, in green you have what happens after an hour, etc., etc. And what's interesting is that when you extract features from accelerometers and project everything on a single plane by utilizing these techniques, Sammons mapping, that maintains the distance in 2 dimensions, that is the distance, or let's say maintains the ratio among the distance that you have in the multidimensional space, that's the one which you have all your features from accelerometers, and you project on 2 dimensions. The distance is maintained, and so what you see on that representation is that points that are associated with the same time interval, they tend to cluster together. And in fact, you can even identify a pattern in which, as the severity of symptoms is changing over time, you're moving in different areas of this feature space. But more interestingly, if you look at the right-hand side of the screen, and if you use a color map that is associated with the severity of the symptom, as opposed to just the point in time where the observations were performed, you see very clear clusters and a pattern of change over time. That is the one that, in fact, need to capture in order to be able to reconstruct what you have on the bottom of the screen, which is changes in the severity of these symptoms over time. So as we started the project by utilizing ambulatory technology, and then in order to be able to move to field type of assessments, we rely on wireless units. These are called SHIMMERs, that were developed by Ben Curris, who was part of the R&D Intel group in Cambridge, Massachusetts, that we collaborate with. And in fact, this was a development that occurred in collaboration with us. So these are wireless units that allow you to implement the body sensor network. They run essentially on Zigbee. They use the MSP430. They do have a 3-axis accelerometer, which is a free scale on the motherboard, and then you have an attachment for a daughter board that can be either gyros or EMG, an EMG board or EKG board. So the board basically interfaces with a variety of different sensing technology. They run at this point in time without sort of duty cycling on the radio. They run on a 250 milliampere hour battery for about 12 hours. So there are still a few limitations with this technology, but this is technology that allows us to gather data over a day through with a sampling rate of about 100 hertz per channel, and not only gather the data through wireless communication, but also has the flexibility of dumping data on an SD card that's actually sitting on the nodes, which is a way to guarantee that even if we have problems with the wireless, because we start losing packets and things of that nature, the data are intact. So if we're supposed to run projection algorithms and look at the graphical representations of features in this feature space, we actually utilize a classifier. Then we can actually show prediction errors. And the errors would be, in this case, discrepancies between the assessment of a clinician and the assessment that is performed by utilizing this sensing technology. So the prediction errors that you see on the right-hand side of the screen that were achieved by utilizing support vector machines. The input is the one that I described before, so features derived from accelerometers. And the tasks that we utilize to predict the scores are tasks that are taken from clinical examinations. And what we're interested into is to figure out whether the prediction error is changing significantly across motor tasks, because this is an indication of essentially whether or not we can utilize this technology to process data that are gathered during simple activities of daily living. So in a nutshell, if you do testing in a lab and you show that multiple tasks can be analyzed in a way that allows you to identify characteristics of movement patterns that are associated with the severity of the disease, that means that you can take movement components from activities of daily living and still being able to actually run these classifications or prediction. So this is very good news to us, the fact that there are multiple tasks for which the prediction error is very small. It's within 10%, which is actually what you would expect in terms of inter-rater reliability when you have multiple neurologists looking at these type of patients. You can see here some missing points. The reason why some points are missing there is because certain tasks are just not suitable to characterize certain symptoms. So all the tasks are suitable for tremor, which is what you see in the top panel, but not all the tasks are actually suitable to assess slowness of movement, which is bradykinesia, which is what you have in the panel as shown in the middle, or dyskinesia, which is what you see on the bottom side of the screen. And let me just comment on B. This is obvious because if you're looking into slowness of movement, if there is no activity performed by a patient, then it's obvious that you can gather information that relates to it. The other thing that we have been exploring in the past year or so is whether there are actually features that we extract from these accelerometer data that are more strongly predictive of the severity of these symptoms. And this is a table that summarizes predictions errors that are associated with the combination of 2, 3, 4, 5 features types. This would be a long story, but just to make it very short. So what we are trying to achieve essentially is to see if there are types of features that we can actually estimate by relying on the computational capability of the nodes as opposed to estimate them offline. So that as opposed to store the entire time series, we can just store features. So this is not possible for all sorts of features, and it turns out, and for those of you who are interested, I'd be more than happy to point you to some of our publications. It turns out there are actually features that can be extracted just on the nodes with very limited computational capability. And they are still highly predictive of these clinical scores to the extent the prediction error is going to be limited to a 10%. What you see in the table here is actually the range. So for instance, for one feature type, if you use one of the 5 types that we have been utilizing over the past few years, the error, the prediction error ranges between 6.6% and 22.4%. And so obviously you're going to pick the one that is associated with the lower prediction error, as long as that's computational feasible with the capability that you have on the nodes. In that case, for instance, we got about a 6.6% prediction error with a feature that cannot be computed on the nodes, but by utilizing a feature that can be computed on the node, the error went up only a couple of points percentage-wise. And so that was very encouraging. So very, very quickly, in the last 3 minutes that I'm allowed, I want to tell you, and I hope I'll be able to convey a bit of